Hello, I'm Rajiva, and I'm one of the TAs assigned for the Big Data and Biological Networks course, and I'll be focusing on the genome assembly module taken by Dr. Nirav Bhatt. So in this tutorial, we'll basically look at what the algorithm is and how we can implement a simple variant of that in Python. So I'll just refresh the basics for you. So your Eulerian path in a graph is a path that visits each and every edge exactly once. And a cycle, an Eulerian cycle is an Eulerian path which starts and ends at the same vertex. So the main application for this Eulerian path is happens in genome assembly, where we like to generate the final sequence from reads. So as I mentioned earlier, the genome assembly problem is to reconstruct the string from its pair reads. So the pair is because of the nature of the experiment, the entire genome is broken down into smaller and smaller pieces which are individually sequenced, which is then finally assembled using this algorithm to generate the final original sequence. So there are many bioinformatics tools available for solving this problem, such as Velvet, Spades, and Abyss. But the main issue with these tools is that they are all Linux based tools, and they're all, more importantly, they are command line tools, which means there is no graphical user interface. So, and moreover, they require a lot of computational power in order to be able to use them. And so it'll be difficult for someone without a dedicated hardware to use these software. So we try to simplify this problem, and using Python, we try to get an idea of how this genome assembly problem works. But if you're still curious, we have included links to all these tools, and you can always go and visit them and improve your understanding. So let's get started with the tutorial itself. So first, we'll be importing the libraries that will be necessary for this tutorial. NumPy, as you all know, is for array manipulation. Then we'll primarily be using NetworkX. So NetworkX is a dedicated Python module that helps us in creating graphs and manipulating and understanding these graphs. And then from NumPy random module, we'll be using a random number generator. And then for plotting, we use matplotlib and Seaborn. So these two are the plotting packages. Next, we just set the theme of the plotting using sns.setTheme and setPalette. So this is just the basics, and this is just initializing the code itself. We run it. Doing this tutorial, I want to create a sequence generator or generate k-mers itself. So I wrote a small function that will generate k-mers based on our input parameters. There are 4 parameters. The first one being n, which is the number of k-mers you want the function to return. K is the length of the k-mer itself, and seed is a random seed that you can use for reproducibility. So if you were to give the same seed as I used in this example, you'd get the exact same result. So it will help you better understand. And then return seek is basically a parameter that dictates whether you want the sequence itself to be returned or if you don't want the sequence to be returned. So in this case, I'll initialize the parameter as false, which means by default, the function won't return the original sequence. And then to generate the sequence itself, I initialize a random number generator using this function. So default RNG from the numpy.random mod package will create a random bit generator, which can be used for various functions such as generating probability distributions, samples based on probability distributions, choosing random values, and so on. So I give the seed so that it's reproducible, and then I generate I create a list of 4 alphabets. So these are all these are the 4 adenine, guanine, cytosine, and thymine. These correspond to the nucleotides that are present in the DNA itself, and then I generate the sequence using this line. So let's break down what this line does. So first we will focus on this part, rng.choice. So in the random module itself, in the random generation, there's a subfunction called choice, which given based on given a list or an iterable, for instance, it will randomly sample as much as you want, as many samples as you want. and the size you can give it as this. So if you recall in the theory classes, we might have discussed that the number of k-mers for a given length of string is given to is equal to k-mers is equal to the length of the string minus the length of the k-mer itself plus 1. So in order to generate the final sequence, we just flip the formula around. So the final length of the sequence should be the number of k-mers plus the k-mer length minus 1. So this way we get a list of all the alphabets that we join together using this string.join function, which will create the final sequence. So we first initialize an empty list that will contain all the k-mers that will be returned in the final result. Then we create a simple for loop to generate each k-mer, and then in each for each I and I plus kth index, so we generate that particular k-mer, and then we append it to the final k-mers list. So the final output after the for loop will be a list of all k-mers that are possible from the given sequence. And then we create the return statement. So if the return seq was true, which means you want the sequence to be returned, then we'll just return both the k-mers and the sequence. And if you don't want it to be true, you can just return k-mers and it will directly return only the k-mers. So we'll initialize this function and then we'll run it. So in this example, I've chosen the seed to be 1 and the return seek to be true, which means the sequence will now return the the function will now return the sequence. And now I'll show you the visualization itself. I'll show you what the k-mer looks like. So we can see that there are 10 k-mers as we requested of size 3. Now we want to represent this k-mer list as a De-Bruijn graph. So for that we'll be using the NetworkX module. In the previous tutorial, you might have come across this graph in NetworkX module called digraph. So that is the default function that will be used to initialize a directed graph in NetworkX. But one quirk of De-Bruijn graph is that there can be multiple edges from one node to another. So by default, the digraph class does not support multiple edges. So to work around that, we have another class called multi-digraph from the NetworkX module itself, which you will initialize. We initialize it as an empty graph, and later we'll add all the nodes and edges into it. So we create a list of all edges possible. So basically, the nodes, if you recall the theory classes, you know that the node should be the suffix of the previous k-mer and the prefix of the following k-mer. And so similarly, for each string, which is for every string in k-mer, I take the suffix and then I take the prefix, and then the label will be the string itself. So that will be the name of the edge itself, and we create a list of all edges like that. And then once we have a list of all edges, we can just use this function called add edges from, which will directly directly read the input and automatically create the graph with all those edges. So I'll just run that, and this just represents the number of edges, and one represents that one indicates that there are two nodes with more than one edges. And then we can visualize the nodes that are present in the graph by saying that the dbgraph.node nodes. So we have these nodes that are present in the graph. So to view the edges in the graph, we use the dbgraph.edges attribute, which will give us the starting node, the ending node, and the index of the edge itself. So 0 means there's only one edge. It's the first edge between those two nodes, and it needn't increase. So now we'll visualize the graph itself, and you can do this by something called the draw functions, which are present directly in NetworkX. You can draw the Kamada Kawai layer. So in NetworkX, you'll have to tell how the graph should be positioned in the the final figure. For that, there are different layouts and you can explore them. And one such layout is the Kamada-Kawai layout. And you draw the graph and then you set the node size and then you label the nodes in the graph. So if you notice, we asked for 10 k-mers, which means there should be 10 edges between all the nodes in these graphs. But if we count, there are only 9 edges. So the reason that is because, as you can notice, as I told you in the previous cell here, between TT and TA, there are 2 edges that is not properly visualized. And now we'll discuss how to properly display all the other edges as well. How we'll correct it is by we'll write a small code where every other edge other than the first edge will curve it by a small amount. And I wrote a simple code to do that. It's quite easy to understand, and then you do that. So now we properly plot the graph. So by default, NetworkX does not have a function where you can label the edges themselves. So I've just written a small function that will help you do that. And so we first initialize the figure, then we switch on the axis because that is irrelevant to this this plotting event, and then we create a variable called pos. So this will represent how the nodes in the final figure should be positioned. So one layout that you can use is the circular layout, which is directly present in NetworkX. And as discussed earlier, Kamada-Kawai is another layout that is being used. And then you first create that layout, then you draw the labels. So you basically labels those places. Then first you draw the straight edges that was defined in the previous cell, and then you draw the curved edges, and then you draw the nodes themselves, and then we label the edges using the function. So I'll just show how it looks like. So now it's much more clearer and we better understand what the graph is like. And now we can also observe that there are two edges passing from TT to TA. So now we are able to properly visualize the graph, and in this graph we'll now try to extract the Eulerian path. So for that, there's an inbuilt function in NetworkX called nx.Eulerian path, for which you give the graph itself and you set this keys argument as true, and it will create a generator, and then you can use a list comprehension to find the list of all edges that has to be traversed in order to traverse all of them. The order, so basically what this function does, that it gives you the order of edges that to be traversed in order to cover all of them. So now we can see that from GC we move to CT, we traverse one edge. From here we move to TT, we traverse another, and then TT to TA, TT to TA, then TA to AA, then AA to AT, from AT to TT, then TT again to TA. Now we go to AG, then GT and TG. So this is what the path also suggests. So, and now we've shown that we can generate the Eulerian path using the NetworkX.Eulerian path function. Now we'll try to reconstruct the original sequence and we'll observe what happens. So I've written a small function to generate the final sequence from the Eulerian path list. So I've generated this function called generateSeq, which takes in the path as input, which is basically a list. So we'll need to give this list as an input. And what this function does is, first it will initialize the first 3 letters of the sequence, and then from the next k-mer to the end of the path, it will continuously append this list to the sequence to generate the full sequence. So we'll generate this, we'll apply this function on the generated sequence. So we get this sequence. Now we had we got a sequence SL. Now we'll compare these two, and as you can see, they're identical. So we were able to generate the the original sequence from the k-merged CIF. So I hope you you got a bit of an understanding of how this algorithm works, and thank you.